Okay. So in this second session, it's basically two parts in the second section. The first part is about modern CMake. This is somehow, again, the same thing as we already discussed in the first part, just with more focus on the modern CMake part. This, I think, will be useful for all of you because we kind of revisit all the patterns that we already seen before, and we go through all the functions again. And the second part is somehow we dive into more details of the find package. So we are going to look at how can we write our own find mylib.cmake, so like find boost before. We are going to show you how you can write it for your library, which basically means how can you find a package which is not written with your own CMake list.txt, but it's an external package. How can you find it, and how can you integrate it into your package? So we are going first to modern CMake. What is modern CMake? Does this work? Okay. So modern CMake started around CMake versions 2.8 to 3.0, which was around 2013. It was introduced by Stephen Kelly, and I found a quote where he said that he introduced modern CMake as CMake with usage requirements. We are going to look at what usage requirements are. And the main points of modern CMake are that we are looking at targets as the main building unit of CMake. So we have libraries and we have executables. They form a graph, this dependency graph that we have seen before. We will see it again afterwards. And we are just saying what are the dependencies among those targets, among those nodes, and what are the compile options and all the properties of those targets. Another thing of modern CMake is that we have this find star files, so this find boost or find whatever, they already existed before, but now they provide targets. So we can link against boost : program options. And before, when we did a find package boost, this only provided us some variable like boost include dirs or boost library or whatever. And then we had to manually take care of that and build them into our CMake. So one of the main conclusions of modern CMake is that we need to avoid functions like include directories or all of those functions which are not bound to a certain target, because they are considered bad practice, because we want to have our options and all of the flags and all of that should be bound to a certain target. So we are looking here at an old style CMake. So you can see here some problems in this, or what is considered bad practice. So there is first, we see here the include directories and the, okay, do you see it? No, you don't see it. Okay, the mouse doesn't work. Oh, sorry. Okay, makes sense. Okay, the include directories and the link libraries and also the add compile definitions, they are all of them are not bound to a certain target. So when we set use CUDA, this will be this definition, so this define will be applied to all targets in this directory where the CMake list.txt is. And also the include directories will be, so boost is basically linked to all targets in this directory. When we compare it to modern CMake, which is this thing here, we are looking for, looking for boost with program options. We say that it's required, but this time it's going to provide us a target called boost program options, and we are going to link against that. And when we link against boost program options, we directly get the include directories from boost, and we get the link, so that we get the libraries from boost and all of that. And the use CUDA, which we had already before, there in the bottom, this is also specific to a target, so we are using target compile definitions and not add compile definitions, and we directly bind this option to mylib. Okay, we are quickly changing a bit, completely changing the topic, but we are coming back to the targets just in a second. a file structure. Somewhere is also mentioned in the comments what you would like to learn here. You would like to learn what's a good file structure. And this is kind of a proposal how I would structure it and what I think is a good structure. So in a good library, first one very important thing is the include, which is here. The include is a separate folder. So all public headers, which means the headers that you need from the other libraries, they're in a separate folder. They are not in a normal source directory. And in this include directory, you usually have, again, the name of the library, because then you can just copy this folder to wherever you want, and that's it. So it's very easy to install. All internal headers are in the source directory, like an internal header here. They don't need to be copied when we are going to install the library. And also the sources are in the source, and then we have some other folders like tests or documentation. And another thing is where you want to place the CMake list.txt, and in general you should place them in all directories. You should have, so if you have the source directory, you should have a separate CMake list.txt there. If you have several folders there, each of them should have a separate CMake list.txt, and you just refer to them with add subdirectories, as you have seen already before. And in the include, there is no CMake list.txt, because you just want to copy this folder and don't care about anything. And there is also the CMake folder, where you find some helpers, maybe, that you can include with this include command. Or there are these find star files where you can find that you can include with find package. So in this case, this is find another lib, which is for find package another lib. And important, in order to make this work with the CMake folder, you usually will append the folder of will append the CMake folder to the CMake module path, which is a path that is already defined by CMake. So back to targets. What are targets? So targets are kind of building this graph that you see in the bottom. So we have nodes. These are the executables and the libraries. And we are now needing some information about how can we build those nodes. So how can we get an executable from, what do we have, sample 9 unit test. So we need to know what is the build type of this thing, which the library is an executable. We need to know the flags. We want to compile with standard 11 or whatever. We need to know the include and link directories, or also the libraries, where they are and how to link against them. We need to know which compiler do we not want to use, which link are we going to use. And of course, very important also, what are the dependencies, because we need to know what needs to be compiled before what. And each target has properties. This is just some list of properties that each target has, and we can set those properties. So for example, we can set the property compile flag of the target my target, and we can write there dash minus flag, dash my flag. So we will compile my target with minus my flag. And all those target compile options, all those target commands are just abbreviations or shortcuts for the set target property. So they are just setting a property, some string, connected to that target.
Question?
Yes?
If I have to use the microphone, I better. So when you say that the set target property, target compile options is just a shortcut way of doing the target properties. Now, sometimes when you do, for example, set target properties, you've got minus my flag. Mm-hmm. And sometimes you do minus d something 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 equals something something. And is there a difference in the way when you do target compile options and target properties that you don't necessarily have to put some of the minus d's and the things, or
for the compile flags, this compile flags is really the flag. So compile flag, when you would want to specify minus d something, it would always need to be there. But there is another property which is compile definitions. This is also a property. And there you can specify it with -d or without -d, and it doesn't matter if it's in properties or with target compile definitions or whatever it's called. So it's really just a shortcut. It does exactly the same. Related to this, there are different scopes. So we have already learned about 2 different scopes that are there. There is a directory scope, exactly. The directory scope is what we said with this old-style CMake commands like include directories or link directories or whatever. Those are, so when we set include directories for a directory, this include directory will be an include directory for all targets that are defined in that folder. Another scope is a source file scope that you can set with set sources properties. And also there, I mean, you can specify all of those things like include directories or compile options or compile definitions or whatever. You can set them for each source file separately, or you can set them for all targets in a directory. And the third scope is the target scope, which is the one that we are most interested in. So you can set a compile definition that is for all source files in a certain target. So those are the 3 most important scopes. And basically, directory scope is the old-style CMake way to do it. And the target scope is the one that we try to use today. We've set target properties or those shortcuts like target compile options. There are also other scopes for tests, and there is a global scope which only has 2 properties or so, which is not really important. Then there is the question, what will be the final include directories when we are going to compile certain files. So we are going to compile f.cpp. We now have these different scopes. So we are first looking in all include directories that are in the directory scope. We extend it with the target scope. We extend it with the source scope. And also for the other properties. So with an example here, we have add compile definitions, which is a directory scope. We have the source file properties, which are different for a.cpp and b.cpp. And we have target compile definitions, which is a property on target level. And when we look in the bottom, we see that first, when we compile b.cpp on the bottom, we will compile it with file level b. So this one is only used for b. The directory and the target levels, they are for both of them because they are in the same target and in the same directory. And the order is from the least specific, which is the directory, to the most specific, which is the source. So this one comes last. And this holds for all properties. Then a very important one I already told about is build requirements or usage requirements. This is something which is really considered the modern CMake. So this is why all this started. I'm sure you've already seen this somewhere, that you can specify things as private, as public, or as interface. And the thing is that when you have something which is private, this is a build requirement. So when you have private, when you have a define which is private, this will only be used when you compile the object file itself. When you link it against another file, like here, okay. Here we have D1, which is private. When we look at the bottom, D1 is used to compile lib1, but it's not used to compile lib2 because it's private to lib1. And when we link it against another file later, it will not be used there. So this is a build requirement and only used during building. A usage requirement is the complete opposite. This is something that we don't need when building the thing itself, but we need it when we link it against something else. So this is something that we need when we use the library. Like here, D3. D3 is not used when we compile lib1, but we use it when we link against it. And D2 is the combination of both of them. It's basically this. And very important, don't use public for all of them. You can use public for all of them. It should usually work, but it's for sure not what you intend. For example, if you have a build requirement linking against Boost program options, you probably want to make this private because if you share the library, you don't want to ship Boost program options with it.
But this is a requirement. I mean, program options is a header-only library, but if it's not header-only...
Program options is not header-only, is it?
Header-only, then you need to make it.
Okay, yes, that's true.
Because, I mean, the linker needs to know all the dependencies and not only the one that you directly link.
Unless you use our path, probably.
If you use our path properly, yeah, but I mean, normally you need to tell the linker all the dependencies. So if you're
yes, but for defines it for sure makes sense. For defines
if you build lib1 and you say privately, I'm using Boost program options, if you don't expose any of the interface that requires Boost program options, then somebody who links against your library, CMake will handle internally any of that. I mean, the linker, it doesn't need to explicitly link program options to their binary, as long as the original library that they've built has linked properly. So in that case, it's whatever. Yeah. I must admit, I very much like this slide because I've never seen those colors done the way you've done D1, D2, T3, and I suddenly think, okay, I never used interface ones before, and lovely.
Thanks. So this is the full list again, as you've already seen this, the commands to set the properties for targets. So you can see this as objects. So libraries and executables are kind of objects. So these are two different kinds of objects that we support. There is a third one, which is not really something that we use. These are custom targets. And the other ones are kind of methods. They just set something on those targets that are the objects. So the link libraries say what libraries we are linking against. Important there is that you can skip the public or private, but you should probably not, especially if it's a library, because if you use target link library once without public, private, or interface, you can never use it afterwards, which is kind of odd. Target link options is to set custom compile options. This is a very new feature, so if you have an older version of CMake, it's probably not yet there. Include directories is clear. Compile definitions is for preprocessor definitions. Compile options is for things like, I don't know, F exception, I guess, or something like that. And compile features is something that we'll probably mention tomorrow. And again, try to set the properties on target level, not on directory level, and usually also not on source file level. Again, prefer target compile options to set usage requirements. So when you want to compile something with we-all, it's probably not a usage requirement, because you don't need to compile with we-all to compile something. So this is probably not a usage requirement. What is usage requirement is something that you really need to use it. So f-elite constructors is something that changes the behavior of the compiler, so you need it there. Also, -03 is not a usage requirement. This is something that you can set with the build type. So really only make usage requirements for things that are really needed. And again, don't use add compile options because those are not target level. Also, don't use CMake CXX flags for usage requirements because those are not meant for that. Usage requirements needs to be applied to the target itself. And CMake CXX flags is something that the user probably sets when he wants to use CMake, when he wants to use your project, he's probably set CMake CXX flags to -v-all or something like that. This is how the user will say, I want to compile with v-all. Another thing, target compile options shouldn't be used for compile definitions because there are a separate function for that, and also compile features. And this is just for reference it's probably, if someone is already a bit advanced in CMake, sometimes you have the problem that you want to have two options are tied together, so -x compiler is a very common thing. And if you don't write this shell colon in front, it might just drop the X compiler if you have something like -X compiler my flag, and later again -X compiler something else because it deduplicates the whole thing. So then you have this shell colon thing. Interface library is the last thing that I want to mention for those for those modern CMake stuff. Interface libraries is a special type of libraries. So there are shared libraries, there are the dynamic libraries in CMake, and there are the interface libraries. And interface libraries are libraries which don't have any sources, so they don't need to be compiled. They are just a collection of usage requirements. So they are something like, okay, when you link against me, you will get -d something, or you will get some options. And they are mainly used for header-only libraries, but you can also use them for things like, in our case, for example, we have a separate interface library, which is called test or something like that. And we have different such test interface libraries which set certain options, and when we link against them, we get those definitions from them. So they can really be also a collection of usage requirements, so they have certain defines connected to them. We can just use them. And of course, they have no build requirements because they are header only and they are not compiled at all. So yes, this is the part about modern CMake. Are there any questions about modern CMake or about what we had until now?
Could you just go back 2 slides?
2 slides, here.
Just tell us again, what's this shell thing you said there?
So the shell thing is if you have 2 compile options, and for example, if you're compiling with NVCC and you want to pass something to the compiler, you usually use this -X compiler. And if you have 2 options that you want to pass to the actual compiler, so you have 2 -X compiler something, what CMake does if you don't have the shell, it will deduplicate all options that you pass. So you have -X compiler minus my flag, -X compiler minus another flag, and we'll deduplicate that, and you only have -X compiler my flag, my second flag. And this doesn't work.
Is there an example of this in any of the examples later?
I don't think so.
Because I've used Xcompiler when I'm using CUDA, but I never thought you could use it in other places, so I'll speak to you later.
I can show you for sure an example where we use it. So, okay, let's continue with the find package modules mode. So what happens when we write find package boost 157 require? So we are requiring boost with a version 1.57. So we are trying to find a file which sets up the target and its properties. So we're going to try to find a file. There are 2 options. There is this config mode and there is this module mode, which are used depending on what library we have. So if we have a library where we use CMake itself, then we try to use the config mode, which we will discuss tomorrow. And if the library is not using CMake itself, then we are using module mode, which I will show you now. And okay, first it will try config mode, then module mode. This is usually not really a problem. What is a bit tricky is there are 2 signatures of find package. One is very long with many different options where you can pass options like hint or path or names or whatever. And if you use something of this long signature, it will automatically be the config mode. So what's module mode? Module mode is used when you have a package which usually is not built with CMake, because then we cannot use the other mode, because then we need to have CMake to support config mode during building the other library. And when we are in the module mode, we are going to look for a file which is called find mylib, find boost, whatever. And we just need to find this file, which is usually pretty simple because there is only a limited set of directories. We are going to look for it. And this thing needs to set up our target. So the file will do something like it will try to find our libraries. So we have find boost, and it tries to find where is boost. Is it installed in user lib, is it installed wherever. It will check if it will abort if required was passed to the find package. It will say if it's found or not, and it will create, most importantly, it will create the targets. So find boost will create the boost, the colon program options, and this is what it needs to do. So this is really the most important thing. And also very important, CMake is not checking if the module has been loaded correctly. So you can do find package boost, and it will not set boost found. It's still okay. CMake doesn't care about that. So what's very important is find boost doesn't know anything about where boost is. So boost can be anywhere, and we need to somehow guess where it could be. So it's really about guessing. So we need to know how can we guess where boost is. And there are different options what we can do. So first thing is we can ask the package manager. So package manager might be installed via the package manager, so we can ask him, where is it installed, give me include directories and all that stuff. Second thing is the user can be installed by the user. In that case, we might ask the user, where is boost installed? So the user will pass us boost root, and we know, okay, boost root lib something, this will be the library. It couldn't be installed at a common location like user include. There is usually, maybe we are lucky and we find there boost config.hpp. Or we can also have some random guesses because we know, okay, this library is usually installed at a very certain place, so maybe it's there, and if you're lucky, it's there. So find package module mode, in contrary to the config mode, is about guessing where the library is. Usually the other one is more about the user asking where is it installed, where is the config mode, and there is everything is written there. So what find package needs to do, it needs to find, for example, the boost program options, the shared library. So we need to find some of these artifacts. So again, it's about guessing where the libraries are. And there are some helpers. There are find library, find path, find file, find program, which all find certain things. We are trying to find config.hpp in a certain folder. We are going to find a library with a certain name. And they are all sharing the same signature, more or less. We can give it some hints. We can give it some paths. And it will try to find it first in those locations. And if it succeeds, it will create a cached variable with the same variable name, and the user can also change those variables if the guessing it was wrong. And there are, as you see there are hints and there are paths. Both of them look very the same, but they are more or less the same. So hints are usually used for kind of educated guesses because we have already found something else, so we are relying on that. Okay, we know where this is, so when this is there, the other one might be there. So hints have more priority and are kind of educated guesses, and paths are just random guesses somehow. And it's a really complex search procedure, so when you look at the documentation of find package, there is quite a large list of different paths and options that might be searched, and there are really many things. So what's a good first guess? Where might we find something? So we can ask the package manager. So there is this package config thing. This is, I think it's quite distributed this is quite common to all Linux distributions. This is a set of files that are written when we install something. For example, for lib input, which I take as an example here, there is a file somewhere where it's written what is the library directory, what is the include directory, and we can make use of that file. So if we have a module that is most likely installed with a package manager, with apt-get or whatever, we can first find package config, which looks for package config for this executable, and package check modules will check for a lib input, which is the name of the package, and we can also restrict the version. So we can say, okay, I want to find lib input with version larger than 1.6. And when I do this package check module, this will create a set of cached variables or internal cached variables. and will basically just transform the left-hand side into the right-hand side, and then you have good guesses. So if it finds this, then maybe if I'm looking for a library, then I will look at user lib, because this is where it's installed. So very important, don't trust this result, because you should just use it as a hint. So still use find path afterwards, or find library, or whatever. With find path or find library, we can then reuse that. So if you're going to look for an include directory, we will try to look for a file which is called libinput.h. And as a hint, we give include directories, because this is kind of an educated guess, because we know that it's installed there, so it's very likely to be found there. And also for find library, we do the same. There we are looking for a file which is called input, and I think it's also looking for input.iso and whatever. Handle arguments. So what's a bit the problem with this module mode is that it's quite complex, because we need to take into account all those options like required or quiet, which says that it shouldn't print anything. You need to do version matching if the version is matches the version that is given by the user. So there is a helper which is called find package handle standard args, which takes for you the button to check the version, which takes you all of that, which makes all of those argument handling for you. You can also do it yourself, but with this it's much easier. So this is kind of what you write. You do the find path, find library as before. Quite important is that you try to mark all options as at once that are not really important for the user, because in general he shouldn't change them. He might change them if he knows what he does. So in the CMake, you will usually not see advanced entries, which makes it much easier for him, because then he only has the important stuff there. We can write the version that we have. Then we do the include, this find package handle standard args, and we call the function with required vars, which means that we need to have found those. If those are not found, it will complain to the user with, OK, this variable was not set. Please give me the include directory, and the user needs to give it for you. And probably we also found the version, so we will pass the version, and it will check if the version matches what the user expected. So it will check if the find package is really returning what the user expects. And this is an error message that we might get. So could not find mylib, missing mylib include here, mylib library. So it was not successful. So the user needs to specify the include directory himself. So there are these cached variables where the user can change something. So for example, the library or the include directory. And there are some name conventions, which are those here. Mylib library is the path for libraries. Mylib include dir is usually for the include dir. And it's not, and I write this explicitly here because I'm always confused by what is what. It's not mylib libraries and not mylib include dirs with s in the end, because this is not the cached variable. This is usually used as the final set of libraries. So when you did find package boost in the old style CMake, this usually gives you a variable called boost libraries and boost include dirs. But this is not the same. This is kind of the old style CMake, and this is not a cached variable, so this is not the right name. So you should use the first version. And try to keep the number of cached variables as small as possible, because if there are too many, it's hard for the user to understand. But you should give at least once by convention, because if you don't give the user one option to set at least one library or whatever, there is no chance for him to fix if he has a problem. Because, as I said, it's about guessing where the things are, so you need to give the user the option to say where the things are if he knows what it is. Mark them as at once, this I already said. And in the end, we know where the libraries are, we know what include directories are, so we need to create the library itself. So what we can do is we can create the library as normal, with the only difference that we write interface imported, so it's an imported target. We can set some compile options, like here, again with the shell xcompiler flag 1. And we can link it, and in the end, we can use this lib, : lib, as a normal library. Important is that if not target lib, the user might do find package lib several times, so you need to check if it's not already created, because then you would have a problem. And just to mention again, because this one has I've seen before several times, endif is also a command, and this is the reason why you also need to add the parentheses after endif. So if and endif are commands, so you cannot just skip the parentheses. Okay, didn't know that I added this. You need to assume that it might be loaded twice. Yes. There is a slightly different option. You can also do, so here we had interface imported. It's not really an interface library because there is a library attached to it. So you can also use unknown imported, which looks more or less the same, except that you need to specify all properties manually, and you cannot set them with the nice target compile options, all of those, but it's slightly more precise to what you want. Last thing altogether, so we are now able to write such a module file. So what we do, quickly go through it. In the top, we first are going to ask the package manager if he knows that this thing is installed. Then, based on what he said, we are trying to find the right include directories and the libraries. We are doing the find package handle standard args, which takes care of if it was successful and if the version is the right one, and if it's what is required and it was not found, it will complain to the user that it was not found. And afterwards, we are checking if the library was already created, and if not, we create it, and we set the target properties, and in the end, we mark all options as once because we don't want to expose too much information in CMake. Questions?
So let's say we make some bad guesses with this find, and it doesn't work for the user. Is then the conventional way for the user to point to the right? Sorry. Is the conventional then for the users to use the CMake to edit manually the libraries and the include dir?
So there are two options how this can be done. The first option is if you just install the library and you just one time you want to adapt them, you will go to CMake or open the CMake cache.txt and you just set those two things to the right one to configure generate and it will work. And the other thing is that before calling CMake at all, you can just pass it, you can just define libinput_library. So you do CMake --d libinput library equals path to the library minus d libinput include dir equals path to the include directory, and will work because then it will not do the find path at all. So these are two options. The second one is probably the one that you use when you use it regularly or in a script or whatever. Other questions? Yes?
Not really a question, just a remark to it. So there is also the option, if you install things in non-standard directories, then what I usually do is just export environment variables. And CMake has this convention that boost_dir as an environment variable will also be used during this find package boost, right? So this is another way how people usually work when they use CMake.
Anyway, all of those options, those here can be used as environment variables, because if you're looking for a variable and it doesn't find the variable, it will always use as a fallback. It will check also if there is an environment variable.